Alright, applications of indefinite intervals. These are called what are called initial value problems. The reason why is because you have to be given an initial value. Alright, suppose that we know for sure that the function we're given is a rate of change function. It's a derivative. So we're given a first derivative. It could be a second derivative, but right now we're going to work on the first derivative. So given a first derivative, we can find the original function we're looking for by using indefinite intervals. Now, we have to also have another piece of information, which is why it's also called initial value problem. We have to have some number that we know is on our original function, because remember, indefinite intervals find the infinitely many possibilities. To find the one we're looking for, we have to have some type of one more piece of information. It's kind of like when we're finding an equation of a line, we have to have 2 points. And the same thing here. I have to have a derivative and a point on my original function. Alright, so in order to find my original function f of x, we take the indefinite integral of the derivative. We get f, which would be, again, my general antiderivative. It could be any antiderivative plus a constant. Alright, so my original function equals any antiderivative plus a constant. Now, this is all possible functions with the derivative that we are given, with this given derivative. When we're doing these applications, we want a specific one. We want one of the infinitely many possibilities. In order to do that, we have to figure out, well, what that unknown constant is. How do we figure out the constant value so that we get the specific, unique, original function to go with our information? Well, we have to be given one more piece of information to do that. Right? We have to be given what's called an initial value. Some point on my original function. Some function value where I know when x is this, my function value is this, my y value is this. And so we have to be given either a point on the graph or given the function value, which again, it's the same thing. It's just 2 different ways you can be given the same piece of information, right? F of A would be the x part, equals B would be the y part. So f of A equals B is the point AB on the graph. And then you use that information and plug it into our general antiderivative to solve for the constant that we're looking for. And again, that will give us the specific constant that goes with our information. Alright, so we're going to do first a couple of examples, just general examples, and then we'll get to applications where this is applied. There are actually a lot of initial value problems. Right? This is one of the bigger types of applications. Alright, so suppose I know my derivative, my rate of change. Alright, so I know my derivative is 5x squared plus 3 minus 7. Alright, so that's my slopes, right? Rate of change. That's how fast my function is increasing or decreasing at any given time. I also know that my original function's value, when I plug 1 in, I get 9 out. So again, that would represent the 0.19, right? Find that unique, and it is unique, there's only one function who has the derivative given, the 5x squared plus 3x minus 7, and has the 0.19 on it. Alright, so first, we find all possible antiderivatives by taking the antiderivative of my derivative. So I integrate the 3x minus 7 with respect to x. So again, this gives me all possible answers. So I get 5x to the third divided by 3 plus 3x squared divided by 2 minus 7x plus some unknown constant. Right, so that represents all possible functions. This is all functions that have that derivative. Right, so it's all of them. Now we want the specific function that has that derivative, and when I plug 1 in, I get 9 out. And then this is going to actually, a lot of times these come to ugly numbers. It just happens to be ugly. But you have a calculator. You can find ugly fractions. And so what you do is, I know when I plug 1 in, I should get 9 out. And so that's the fact that we're going to use. 9 should come out when I plug in 1 for x. So we take x and plug 1 into it. So I get my 5 thirds times 1 cubed plus my 3 halves times 1 squared minus 7 times 1 plus c. And now I solve for c. So what you do is, you simplify this side over here first, right, where you plug 1 in. And you get to use your calculator. It is an ugly fraction. When you When you add and subtract all of those together, it comes out to negative 23 divided by 6, and it's exactly, leave it exact. You have a fraction key or calculator, use your fraction key. And then I'm going to add that 23 over 6 over here, and so my constant, again, it's an ugly fraction, 77 over 6. And so there is the constant. There are infinitely many values my constant could be. But in order for 1 to go in and 9 to come out, in order for this to be true, my constant has to be 77. So my final answer is, then the function we're looking for, f of x, is 5/3 x cubed plus 2/2 x squared minus 7 times x plus 77 over 6. This is the only function, alright, it's the only function that has this derivative, and you can check to make sure it's a derivative, and it is. If you take the derivative, you get that out, and when I plug 1 in, I get 9 out. Right? So that's the only function that has that derivative, so f prime of x is the derivative we want. 5x squared plus 3x minus 7, and when I take 1 in, I get 9 out. Alright, both of those things should check with my final answer, and they do. They both check. Alright, let's do the second example. And then we'll get to applications in the next video. Alright, so suppose this is my derivative. My derivative is 5e to the 2x. Right, that's my rate of change. I also know the point on the original graph. If I plug 0 in, I get 1/2 out. Alright, so again, this would be when I plug 0 into my original function, I get 1/2 out. 0.5 or 1/2. Alright, so first step though is find all possible antiderivatives. So I integrate my 5e to the 2x with respect to x. So f of x is equal to 5e to the 2x. But don't forget, you're not done yet, because when I took, this is the derivative. When I took the derivative, I would have multiplied by 2. Well, to undo that derivative, I have to divide by 2. And then there's some constant at the end. That's why I have this piece of information to figure out that constant at the end. Alright, so all possible functions with this derivative, 5e to the 2x, right? If I take the derivative of this, I would get 5e to the 2x, right? Plus some unknown constant. To figure out that unknown constant, well, I use this information. When I plug 0 in, when x equals 0, my y value should come out 1/2. My function value should come out 1/2. So 1/2 equals, we'll plug 0 in, I get 5/2 e to the 0 plus c, right? I'm plugging 0 in here for x. So I get 1/2 equals 5/2. E to the 0 is 1 plus c, so 1/2 minus my 5/2 is my c value, and so I get negative 2. Kind of nice, negative 2. Right, because I get negative 4/2, which would be negative 2. Alright, so my constant is negative 2, and so that means the function f of x that I want is 5/2 e to the 2x minus 2. That's the unique function whose derivative is 5e to the 2x and has the point 0, 1/2. Right? If I plug 0 in, I should get 1/2 out. Both of those two things should check. Right? It should check. When I take the derivative, I do get 5e to the 2x. When I plug 0 in, I should get 1/2 out, and I do. Right? Both of those things check. So that's what we're going to get to is initial value. So now we're going to look at applications. So the last thing is applications. So we're going to do that in the next video.